I'm going to present.
Victor, where are you from?
Oh, well, I'm from Peru. I am in
Ah,
Lima.
ok.
Yes.
Y bueno, voy a presentar el trabajo de ustedes, que es Design of a Biomedical Soft Robotic Device for Lower Limbs Mechanical Muscle Rehabilitation and Biomedical Monitoring under Reduced Gravity Space Environment. Bueno, y la lista de autores es muy larga. El primer autor es Víctor y le dejo el escenario.
Okay. So, well, first of all, hello everybody. We're glad to be here with you. Today I'm going to present the project, you said, design of biomedical soft-robotic device for lower limbs, mechanical muscle stimulation, and electrochemical monitoring under reduced gravity space environments. I am Victor Ticllacuri. Well, let's start. Humanity has always wanted to discover, know, and understand, and obviously explore beyond our horizons. Space travel is one of the most fantastic aspirations for humankind, where the Earth is no longer our limit and there is no limitation. Hence, space exploration missions. Sorry. Okay. So, uh, space exploration missions and permanent bases on the Moon, and the first gateway for human space exploration and Mars. The first milestone to become the multiplanetary species for having planned from the becoming decades. However, space is one of the most dangerous environments for future human space travelers due to the extreme conditions such as radiation, temperature, and especially the reduced and hypogravity environment, which can negatively affect musculoskeletal and cardiovascular health in astronauts. For example, generating disease-induced muscle atrophy and impaired blood circulation. In this context, mechanical stimulation allows for muscle development and promotes blood circulation, and has multiple biomechanical, physiological, neurological, and even psychological implications. The mechanical manipulation of human body, um, well, the soft tissues of the human body, I mean, by applying rhythmic force on a specific area of the muscles and skin, generate a focus, orthogonal pressure, which has multiple therapeutic effects. The implications of this mechanical muscle stimulation range from biomechanical, psychological, sorry, physiological, and neurological responses. Therefore, the application of this focused orthogonal rhythmic pressure improves muscle performance by increasing muscle strength, speed, and power. However, conventional robotics are made of rigid materials, limiting ergonomics and safety required from interaction with soft human tissues. It's very complicated because we are made of human tissues, our skin, muscle, and the fat. Therefore, in this context, I mean, soft robotics are very convenient technology for space biomedical applications due to that gentle, safe, comfortable, and ergonomics interaction with soft tissues. Furthermore, this technology allows generating complex movements capable of emulating bio-inspired behaviors with advantageous results in medical treatments. In this presentation, we propose and describe the design of a novel medical robot using soft robotic system for mechanical muscle stimulation of lower limbs during space traveling and maybe future colonizations. The system is composed of soft pneumatic actuators placed on anatomical strategic points which apply focused orthogonal rhythmic pressure to the main muscles involved in the physiological gait. In order to stimulate them and induce the blood flow in lower limbs, we incorporate electrochemical sensors and monitor the performance of the soft actuators. Well, let's talk about the design. The design of a soft pneumatic actuator, or also known as SPA, provides the capacity to stimulate the muscles during the hypogravity exposure to avoid atrophy and promote blood flow in lower limbs. For the fabrication, we use the hyperelastic silicon Dragon Skin 30, that's the name, because of its higher Jones modulus than other silicon materials and also for being ideal for vibrating applications. Additionally, we use the polyethylene terephthalate, or also known as PET, a plastic, to make a zero air chamber and prioritize only one direction deformation because of that. The PET is both extensible and flexible. With these materials and design features, the SPAS is mechanically programmed since it concentrates the deformation energy towards one direction, to the user, and limits the deformation in the direction where it's not required. Additionally, the manufacturing process would be significantly reduced. Well, to sum up, Due to the designed 2D configuration and the combining two hyperelastic materials, the SPA is highly compact, while it's pressurized, as you can see in this image. And also wearable because of being lightweight, and additionally, when the SPA is pressurized, increasing its volume is observed only in the desired direction, making it also highly efficient. The feature was achieved by using the PET foil as a auxiliary chamber and a mechanical programmation performed by varying the thickness of the actuator walls and their materials, as you can see in this picture. TL1 and TL2 are the thickness of the layer 1 and layer 2 respectively. The dimensions of the soft robotics, or the SPAs, were obtained from the anatomical measurements of the lower limbs and based on the design requirements. These dimensions allow the actuators to be placed on the specific structures, the muscles. These dimensions allow the actuator, these dimensions allows the system stimulate specific muscles or muscle groups. Likewise, a vibration frequency between 30 and 35 Hz is used to stimulate the muscles, since at this frequency, not only muscle power and neural motor function are intensified, but it also may improve blood flow, muscle oxygenation in the plate areas, reducing muscle weakness, pain, and inflammation. It's like a massage. It's that works synergistically like a massage. First, this first model has a diagonal arrangement of the actuators for the stimulation of the gastrocnemius, avoiding the pressure of the neurovascular bundles of these areas, working analogously to a peristaltic pump, to induce and increase the blood flow through the popliteal artery and vein, the popliteal triangle. Second, here we can see the arrangement of the superficial stimulation of the semitendinosus and biceps femoris muscles, by muscular overlapping the semimembranosus and the vastus lateralis muscles. In addition, here we can see the second model stimulating the sartorius, vastus medialis, rectus femoris, and vastus lateralis muscles. Now, we had to test the performance of the SPA, so we performed a computational mechanical simulation to verify that indeed the mechanical programming and the design configuration works properly. These were performed using the software ANSYS Workbench in order to apply finite element analysis taking into account the following characteristics. The main material was Duran-Skin 30 with three parameters moniribly. 100 kilopascals inlet maximum performance pressure for membrane chambers. Additionally, we fixed the support in the actuator's extendable lateral sides. But in this picture, you can see a reduced and attenuated displacement on the one side of the actuator conformed by Duran-Skin and Ecoflex. In addition to having the PET foil, with this result, the actuator proves to be able to concentrate most of the energy in the desired direction, generating a higher free displacement to perform better stimulation. Therefore, it will have increased surface contact over the skin, thereby having a deeper effect onto the target muscles, without risking epithelial damage. And as you can see, the more displacement, the better stimulation, and the deeper stimulation. And as you can see, if we increase the thickness of the layer 2, we reduce the stress on the chamber of the pneumatic chamber. So it's not only efficient, but also maybe more safe or safer. In conclusion, the conceptual design of a novel soft robotic system was proposed, focused on mechanical properties using wearable, lightweight, compact, and efficient SPA embedded in a soft matrix, capable of exerting orthogonal pressure to stimulate 8 muscles involved in the gait cycle. Why the gait cycle? Well, one of the most important problems of the astronauts when they return to the Earth is that they can't walk properly because the muscles of the legs are atrophied. So the system could be employed during future Moon and Mars colonization missions. For this reason, it is necessary to be tested on analog space missions on astronauts training on Earth, such as Mars Research Station in the USA or European Astronaut Center in Germany, where also it would be necessary to test the manufacturing and characterization process under those new conditions. On the other hand, the opportunities for applying this technology on the Earth in the clinical area are vast. For rehabilitation patients with muscular atrophy caused by prostrations after traumatic accidents, to physical therapy, for people with muscular diseases or neuromuscular diseases also, and obviously muscle stimulation for people with sedentary lifestyle, such as in work office, remote work, or study from home, as it is currently seen in this time of the COVID-19 pandemic. Well, that's it. Thank you so much. Muchas gracias. Muito obrigado. This is Victor Ticllacuri, and we are Biosynaptics and Space Mechatronics Research Group. Thank you.
Gracias, Víctor. Do you prefer question in English or Spanish?
Both are okay for me. There's no problem.
Bueno, tenemos un tiempito para preguntas. Estuvo muy bien de tiempo, Víctor. No sé si alguien en la audiencia, hablo un poco mientras alguien lleva tiempo a escribirlo. La plataforma no es muy amigable para la interacción. Te pregunto una cosa, Víctor, si entendí bien, todo este trabajo de ustedes está al momento basado en simulaciones. Todavía no han construido el dispositivo para... O sea, ¿cuál es el estado del proyecto en general, digamos? ¿Cómo piensan fabricarlo? Veo que son muchos autores de distintos lugares. Contá un poco más del proyecto y en qué está.
Por supuesto. Gracias por la pregunta, realmente. Bueno, ahora voy a cambiar para el español. Sí, efectivamente, el proyecto ahorita se está basando principalmente en el diseño conceptual y en simulaciones computacionales. Primero que todo, ya que en robótica hablando es un poco complicado pasar a la fabricación en sí antes de haberlo simulado correctamente. Y sí, efectivamente, un poco también por la pandemia, fue uno de los breves limitantes para la fabricación. No obstante, ya se esperaba obtener alianzas para poder hacer esta fabricación principalmente y la caracterización. Como mencionamos en la parte de conclusiones, sí, es uno de los futuros pasos. Y lo bueno de justamente entre todos los autores es de que al ser un campo bastante curioso, al menos aquí en Latinoamérica, sobre ingeniería biomédica aplicada al espacio o aeroespaciales, es necesario tener en contacto con, bueno, varias personas del extranjero, donde ya es un poco más común este tema. Entonces ellos, principalmente entre todos, discutimos sobre el diseño, las posibles aplicaciones y más que todo sentarlo en la tierra para que se pueda fabricar o aplicar. No sé si respondí tu pregunta o desearías hacerme alguna adicional.
No, está bien. Sí, gracias. Bueno, ¿alguna pregunta más del público? ¿No? Bueno, estuvo todo muy claro entonces. Muchísimas gracias, Víctor.